In this video, we're going to talk about permanent dipole-dipole forces such as permanent dipole-dipole and hydrogen bonding. We're going to show you how to draw permanent dipole-dipole forces and how to draw hydrogen bonding. And we'll make sure that you know exactly how many hydrogen bonds that you have to draw. So, first of all, the permanent dipole-dipole attraction is caused by a difference in electronegativity in the actual molecule first. And so we need to identify the dipole in the molecule first. Now, if you look here, these are Pauling values, electronegativity values, and you can see that these are vastly different to this side. You can see this side is metals mainly, apart from hydrogen, and then these are non-metals, okay? If there was a big difference between a huge difference between the electronegativity values, then you get an ionic bond because the atom is pulling the electrons so strongly away from the other atom that actually it gains the electrons and becomes an ion. So as you can see, all of these Pauling values are very much different to here. Now, if non-metals are bonding to each other, as in the NOF clubra, bonding to, for example, P, S, C, and C, you can see that their electronegativity values are very different to the other non-metals as well. So that's when you get a permanent dipole. But why have I highlighted NOF or NOF clubra? Well, that will become apparent later on, but they are all the ones you need to really remember. So NOF clubra is a handy kind of word to remember, NOF clubra. They're all the electronegative elements that have a very different electronegativity to everything else. And it's kind of like an arrowhead at the top of the periodic table. Anyway, let's keep those in mind and put them up into the corner. So they're the electronegative elements, very different in terms of electronegativity to everything else. Okay, and we'll go through some examples. So starting off with hydrochloric acid. So hydrochloric acid, okay, is like that. And we're going to do a permanent dipole-dipole attraction. So we'll draw two. And then at this point, we're going to say, right, where are the electrons? Well, NOF clubra, so Cl is in there, so it has a very different electronegativity to hydrogen, which is not in there. Okay, so we're going to do that as delta minus. So that means a little bit minus. That means the electrons are a little bit closer to the chlorine. Because they're closer, you get a delta minus. And you get a delta plus on the other end. We then copy that over on the other side. And then from that point, we're going to say, well, that must mean the plus of the permanent dipole in this hydrochloric acid is attracted to the negative of the permanent dipole on the other one. And that is called a permanent dipole-dipole attraction. We then go for the next one, which is ICl, which is very, very similar to the one above. So I'm going to draw both molecules out again. And I'm not going to draw the electrons this time because we should know the electrons are moving. And we can see that the Cl is in NOF Cl. The I is not in there, so therefore it must have a very different electronegativity. So we'll put the minus, so that's a stronger electronegativity. It's a weaker. So if it's in NOF clubra, it's always going to be, well, it tends to be the minus if it's bonded to anything outside of NOF clubra. Okay, and then we'll do delta plus and we'll do delta minus. So really important you remember NOF clubra. So that is the electronegative elements. So we look here, electronegative elements, pair of electrons is closer to that end, delta minus. Once we've done that, here's our permanent dipole. We can see there's an attraction between the plus and the minus, and that is our permanent dipole-dipole attraction. Let's pick another example. I picked this one because it might appear in your second year of A-levels, in your A-level exam. And you may not have learned about aldehydes yet, but we're going to do them. And we're also going to do carbon dioxide. So with methanol, methanol is this. Okay, so that's methanol. And the functional group is this CHO, hence this CHO here. Okay, and I'm going to draw another one, and I'll just do it right here. And there you go. And that'll make sense in a second. All right. and I'm going to put the dipoles on. So the dipoles are on, so I'm going to say, right, okay, NOF, as in, O. O is in NOF. It's got to have a different electronegativity to the carbon, only to the carbon. Okay, so that means that will be higher electronegativity, so it'll be delta minus, that will be delta plus. Let's copy this over, delta minus, delta plus. So we've done our dipoles, and let's see where the attraction is going to be. Well, the attraction is going to be between the plus and the minus, okay? Don't worry too much how you draw that out, okay? As long as, so if it's a bit messier than mine, as long as the minus is attracted with a line to the plus on the other one. Really important, don't put delta pluses on the atoms that are not connected to the electronegative element. Okay, that's often a mistake in class and in exams. Don't put a delta plus on the atoms that are not connected to the electronegative element. Now, the last one we're going to do, as I said, was CO2. And CO2 is the one that's sent to confuse people, which they always like to do, stretch and challenge. Okay, and if you look at CO2, you would automatically say, right, okay, that's going to be delta minus, that's going to be delta plus, because O is in NOF, Clubra. So that is going to be delta minus, that's going to be delta plus, that's going to be delta minus. But the truth is that there are two things you're looking for here when you're looking for a permanent dipole. And remember, you can't have a permanent dipole-dipole attraction unless you have a permanent dipole to start off with. And those two things are, the attraction between the molecules has to happen because there is a permanent dipole. We've worked all that out. We've done our permanent dipoles. We use NOF-Clubra to work that out. But you also need something called asymmetry. So if you're not familiar with the word symmetry, if you look here, there is symmetry on this molecule, okay? Symmetry, you could fold it in half, it would be the same. There is no symmetry in any of these molecules, okay? Now that means basically that because we don't have symmetry in these molecules, okay, we are going to give them a permanent dipole, okay? And when I say symmetry, it's not just symmetry in terms of how it looks, it's symmetry in terms of the charges and the electronegativity. So for example here, if you look at the symmetry, you can see that the oxygens are pulling the electrons that way, and the oxygen is pulling the electrons that way. Okay, so pulling in opposite directions. So there is a symmetry there as well. It's not just symmetry in terms of the molecules, so it's symmetry in terms of where the electrons are being pulled. Now what actually happens is that the charges cancel because of symmetry. So because there's symmetry here, the charges will cancel, and therefore overall you will not get a dipole, and therefore you would not expect to get permanent dipole-dipole attractions. Okay, but with the rest of them, okay, you would get permanent dipole attractions because you have asymmetry and you have the permanent dipole. We're now going to move on to hydrogen bonding, and we're going to talk about how to draw hydrogen bonds. So first of all, we need to do hydrogen bonding. We need a permanent dipole attraction requiring, okay, NO or F. So this is why I went NOF-Clubra, okay, because NOF is the elements that you need to get this permanent dipole-dipole attraction occurring. So NO or F bonded to hydrogen. Now, if we're going to do this, what we have to do now is draw a really good diagram for the exams, and it can often be asked in the exam. So let's do it with the most common one, which is water. So there's water, and you can have there. So we look here, first of all, we have to draw the dipole. So the dipole in water is going to be NOF, as in the O is in NOF, so it's going to be the most electronegative element. And both the hydrogens are connected to the O, so they're both delta plus and delta plus. That means the electrons are closer to the oxygen. So we do that, and then we line it up with another water. And remember, just like permanent dipole, we're going to line up the negative with the positive. So I've lined up the negative with the positive. We're going to do that over here as well. And the negative. And then we're going to put all of our charges on. So minus, plus, 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 and minus. So we've drawn all of our attractions. All of our permanent dipoles. Now we need to make sure we draw the attractions. Now the important thing is, and this is really a marking point for the exam, is you must include your lone pairs. Okay, so there's my lone pairs. Okay, and there's my lone pair. There's my lone pair. And there's my lone pair. So I've done all my lone pairs. Okay. All I now need to do is draw the attraction. The attraction is from the lone pair to the positive. So we've got the delta negative going to the positive, and we've got that going to positive. So that is a permanent dipole-dipole attraction of a specific type, which is hydrogen bonding. Okay, so it's really, really good to be able to draw this and show that each water molecule has two hydrogen bonds coming off the hydrogens, and it'll have a further two going up as it continues. Okay, but two hydrogen bonds per water molecule, and that is more hydrogen bonds than in a lot of other molecules, which is why one of the reasons why water has such a high boiling point and melting point compared to other molecules with a similar molecular mass. But let's talk about another common example. So our other common example is going to be ammonia. So we've got ammonia. If we look at ammonia and we do exactly the same thing, I'm going to draw two ammonias. So whenever you're drawing hydrogen bonds, really important thing, lone pairs. Okay, charges. Okay, and after you've drawn them a few times, it hopefully will not be too difficult. Okay, and then we look at the plus and we look at the minus and we go, right, okay, there's our bond. We can also draw it like this. There's a few lines, so you can draw it like that, or you can draw it like that. It doesn't really matter, just be consistent in what you actually draw. And you can see as well, a really interesting thing here is that you're limited by the number of hydrogens or the number of lone pairs on average. So on average, a molecule of water, because it has two delta positive hydrogens, okay, and it has two lone pairs, whatever is the smaller number is on average how many hydrogen bonds it's going to have. So there's two lone pairs, there's two delta positive hydrogens, therefore it'll have two hydrogen bonds roughly per molecule. So again, on average, things will break and form and everything like that. But if you look at the ammonia has one lone pair and it has three delta positive hydrogens. So the smaller number is the number on average of hydrogen bonds that it will have. And so if you look here, there is one lone pair, that's the smaller number, therefore I only have to draw one hydrogen bond. So if you're going to do a proper job on water, draw the right number of hydrogen bonds, which is two, ammonia, one. Okay, and there's two exam-worthy pictures of hydrogen bonding. So this is a good opportunity for you to test what you've learned and draw something yourself. So let's remember our exam tips. Now, exam tip is going to be count the lone pairs, count the delta plus hydrogens, whichever is smallest is the number of hydrogen bonds you draw. Okay, so you make. So let's have a look at our example. Our example is HF. So if you're doing this right now, it might be a good idea to stop the video, try and draw HF, but I'll carry on. So you have HF, and if you draw it, you'll go, there we go, and we've got NOF. Okay, we've got a delta positive hydrogen. Okay, we've got a delta negative there, we've got a delta positive there. Okay, we draw all our lone pairs, so our lone pairs are there. Okay, so we've got three lone pairs. So we then count the lone pairs are three, count the delta plus hydrogens. We've only got one delta plus hydrogen, we've got three lone pairs. So if we're going to draw this, we are going to go for the smallest number. The smallest number is one delta positive hydrogen. So what we'll do is we will draw, let's draw it down here. Okay, and then I'll put my delta negative, my delta positive, and I'm only drawing one hydrogen bond, so there we go, one. Okay, and I've got one hydrogen bond, okay, and that's it. And that is how you draw hydrogen bonds and know how many hydrogen bonds to actually draw.